welcome our next speaker, which is Richard Peters. And we are back with energy again.
Back with energy, yes.
Just quick introduction, Richard, if you let me. Richard Peters has got PhD in vertical transportation. He is a visiting professor at the University of Northampton. He's a fellow of IET and fellow of CIPSE, and he's director of Peters Research Limited. Thank you. Over to you.
I've got the task of getting you to the coffee break without being too late, so I won't go on too much. Thank you for having me again. Thank you for coming. It's great to see you all here today. I'm going to talk about lift energy modeling for green building design, and a lot of what Adam said, just if you think back to Adam's presentation, I follow on from that quite a lot. So I'm very proud that actually I think I was the first person to do a life cycle analysis on a lift. It was back in the late 1990s when I was talking about green lifts, and everyone used to laugh at me when I talked about green lifts. What are we talking about? You're going to paint them green or whatever? But anyway, so and Adam talked about the life cycle analysis or life cycle assessment, which has got a little diagram there from that. And what I concluded at that point was that energy in use was the dominant environmental burden. So actually, the dominant environmental burden of lift systems at that stage, I thought was the energy. Moving forward to 2013, when Dr. Anna Maria Laurenti, who a lot of you will know, she did her PhD in the environmental impact of lifts as well. She also, you can see that at the bottom one is the energy here. It does depend very much on your system. So if you install a system in use is the travel. So this is the energy, basically, mostly energy. And this is all the installation. If you don't use a lift a lot and it doesn't last very long because you've got cheap equipment, actually the embodied energy becomes really quite significant. And that's what Adam talked about. So I'm mostly interested in this bit, and my energy analysis was off the end scale here, because when I did my life cycle analysis, I was looking at a system that was installed and worked for 30 years and got refurbished at about 15 years. Yeah, so my analysis was based on good quality equipment, and that's one message I'd say to you. If you want to be in green lifts, you do actually need good quality equipment. If you put stuff in which only can last 5 years, then that's not environmentally friendly. So moving on to talk about the energy, how a lift works. We operate in what's called 4 quadrants, which basically means we go in both directions, and we motor and we generate in both directions. So there are 4 modes of lift operation. And I'm going to talk about the basic principles of energy transfer in a lift system. And at this point, Lutfi and Rory will think, oh, I know some of these slides, because I actually presented those in 2004 at the LFCon conference. So this is a little bit of a revision, but I thought they were worth revisiting. Yes, we've forgotten about them. So we thought we ought to remind you about them. And I haven't got pictures of us when we were in 2004. That would be embarrassing. This is energy in an ideal world. This is the lift moving in an ideal world. And what happens is the lift goes up and it transfers potential energy. Electrical energy goes to potential energy in the passengers. So actually, in an ideal world, it took 0.1 kilowatt hours worth of energy to raise us up. And at the end of the day, if you've got a regenerative drive, we'll get all that back. So we get 0.1 kilowatt hour back into the system. So actually, sounds good, doesn't it? We don't need, we're not taking in energy. In the real world, of course, we get heat and noise. And on the way down, it takes heat and noise as well. And so there is an overall loss because of those factors. So lifts borrow energy. They have losses, otherwise we'd get all the energy back, and actually we wouldn't be worried about energy in use. That's why we're interested in energy. Let's move on to a real trip. And this is a real kinematics, and you can actually see, referring back to Matthew's presentation, we've got this leveling delay at the end here, and that's, he could model this with his kinematics. And this is the energy of a loaded car traveling up. And this is the energy of a loaded car traveling down. And if we didn't have regeneration, you see this bit at the bottom here, we've got, we're getting energy back into the system. If we didn't have a regeneration, you'd basically look something like that. So we got energy up and energy down. Anna Maria Laurenti did her PhD in life cycle analysis and energy modeling of lifts, and she's presented at these conferences before. So she's the one who produced the graph that I showed at the beginning, and thankfully, I thought I was going to have to do lots of research, but I actually went to her thesis and she'd done it all for me. So she's gone through all of these different energy models that people have produced over the years. And this is, I believe, a full set. Different types of models. Some are based on measurement of a single round trip, and some aim to reduce to rate products based on usage patterns and category tables. And just a side note, Guy D compared two of those models, and there was a factor of 2 of difference. This was back in 2010, I think it was. But as Adam was saying, there's an enormous amount of discrepancy between these models because they make massive amounts of assumptions. Then there was also an empirical model where they basically took some measurements for 6 or 8 buildings, and they just made some estimates based on that, just some empirical calculations. And then you've got the models, the trip by trip models, which again, what was Adam was talking about. And there are three ones that Anna Maria talks about. The Sharif Peters Smith, a model which was commissioned by TK. It's the one we were involved in. Barney made a suggestion. Also, Coney, I believe, has a model which looks at each and edge of every individual trip. So I think, again, repeating what Adam has said, the ISO standard is the starting point. If you haven't got simulation, this is the most accurate public domain energy modeling. In fact, that's what they claim. I tend to agree. They did an enormous amount of work based on enormous number of simulations, funnily enough. So they actually use a simulator to create the tables so you could have this standard. Anna Maria said the most accurate model is obviously the model that we were involved in, but I would say that, wouldn't I? And I will agree with her on that. But it is owned by a company, so there's a US patent on it. And there's loads and loads of maths, so you can go and read the maths if you want to, but it's a really complex model, but it does really work quite well. We're looking at every single trip, so this is a passenger demand profile, and we could, within that demand in a simulation, creates individual trips, and then at the trip level, this is a measured set of curves. So this is the energy consumption going up and down with different loads. And when we calibrate this really complex model, we can get that. So it's very, very close. Compare the two together. So if we have calibrated the model and the traffic is known, we have an accurate model of the lift energy consumption in the building. But what we really also need is a public domain model, because we need one that's available to everyone. And so at the time, back in 2004, I said, okay, well, let's just have an on-off model. And this is what's in our simulator at the moment, just a basic on-off model. So we just draw the lines and we just ignore the going up and the going down bit, the starting and the slowing down. And that's a nice simplistic model. It's available in Elevate. The biggest error, of course, is actually knowing where these lines should be. And getting that data is quite difficult. So I revisited that this year, and I was thinking, actually, we could do a little bit better than that. Rather than just going constant demand, we could actually rise and fall to it. And what this does, it removes the, you don't see the kinetic energy bit. So as you start, you offer kinetic energy to the system. And as you slow down, you get that kinetic energy back. So this misses that, but actually it cancels itself out because you get it at the beginning and you lose it at the end. Yeah. So it doesn't look quite as close, but it's still relatively accurate. And also the jerk you don't see. So this basically assumes there's an infinite jerk because I'm increasing that it's a straight line. So we did a few samples and just looked at the comparison between the, assuming all the same other input data. This is the measured is the orange, the ThyssenKrupp model that we produced is the blue, and then the gray is the this revised straight line model. So to conclude, energy and energy models are important if we're serious about our contribution to the environmental impact of lifts. We need to consider energy models. If you don't have simulation, use the ISO. The nice thing about it is we can all use the same standard model. There are many models out there, but this is, I would agree, is the most authoritative of the lookup models. If you want accuracy as opposed to rule of thumb, then you need to use a trip-based model. And I've like the one that we produce with ThyssenKrupp, like the simpler one that we have in our simulator, and will be improved with this up and down. Also, I believe Coney do one, and Barney also proposed one. So we can do that, and we'll get more accurate results. We do need to collect and share measurements as a matter of the course. It's really difficult to get that data that I showed you. Actually, what is the load on the way up and on the way down at these different car loadings? That's the data we need. And if we've got that, we can calibrate models and get a really good estimate of the energy consumption during the lifts. This is possible now. And that's actually why one of the reasons I come back to it. With IoT, there's no reason why we can't be specifying and collecting all of this data. And I think that leads on quite well to the next session, which is IoT. So after we answer some questions, if there are any questions, then and then we can have a break and we can talk about IoT.
Thank you very much.